So now let's take a look at the code to test the quality of the synthetic data we have been able to generate. We will focus on the process and not so much on the results, as we have used a little amount of data and small recurrent neural networks and just a basic training on a laptop. So the authors talk about 3 steps for testing the quality of the synthetic data. They talk about diversity, fidelity, and usefulness. And the way of checking these points is by visualization, by using a discriminative score, and using a predictive score. So let's start for testing for diversity using visualization techniques. So we will apply dimensional reduction algorithms to our data, synthetic and real, and let's try to visualize how close they fit together, visualizing the result. So we are going to load our data. We load the synthetic data. Remember, we had rolling windows of 24 time steps with 7 dimensions, and we don't really need 24 steps or rolling windows. We just need time steps with the 7 different prices of different crypto assets, or let's say 7 dimensions. So we are going to reduce the data just to 7 dimensions. For our real data, we've got already the same format, 7 dimensions, and time steps, 2400 time steps, and 7 dimensions. To reduce the dimensions of the data, we will use 2 algorithms. First, we will use the principal component analysis, and then the stochastic neighbor embeddings. For the principal component analysis, as this is a linear technique, we are going to fit only the real data. And then we are going to transform the real data, and with the same transformation, transform the synthetic data. So the principal component analysis tries to get the axis which captured the biggest amount of variance for our data. We will use only our real data for finding this axis with the maximum variance, and then we will transform the synthetic data with the same transformation to the same, project the synthetic data to the same axis and check how close they fit together. If we proceed this way, we can plot the results, and of course they are not very promising because we just used a little amount of data, but even so we can see that it's not so bad because the limits of the clusters, they are not so far away, and even here the borders, they kind of are almost the same. So this is just the process. And then let's go to the stochastic neighbor embeddings. For this algorithm, as this is a non-linear algorithm, is different than principal component analysis. The stochastic neighbor embeddings is more based on preserving the local structure of the data on a lower dimensional space. So what we have to do is to put together the real and the synthetic data, and this is what we are going to fit to our algorithm. We choose 2 dimensions and we fit the full amount of data, real and synthetic, and transform the full amount of data. That allows us to check how close all these data they are one from each other. And if we do so, we can check the result here. Plotting is also not so promising, taking into consideration the little amount of data, but it's also not so bad. We can even see some kind of clusters trying to mimic on the same positions. Okay, giving some imagination maybe, but it's not so bad. Of course, after training with a bigger amount of data for a large amount of epochs, we could reach some results similar to the one shown in the paper, as they show here. For the TimeGAN, you can see how the original data and the synthetic data almost fit on the same clusters. Next, let's go to check for the fidelity. We are going to use a discriminative score. And what we are going to do is we are going to label our real data as real, synthetic data as synthetic. And we are going to define a basic neural network, a classifier that is going to try to distinguish between real and synthetic. We are going to train this classifier with some amount of the data and keeping apart another little amount of the data for validation. And we will check if this classifier, after training on real and synthetic data, is able to distinguish between them. So, as you can see here, just combine the data. We've got real data, 3000 time steps with 7 dimensions. We've got also our synthetic data, almost the same amount. We just combine data. As you can see, we are going to have training data, 2000 samples of real labeled as 1, and fake data, synthetic data, 2000 samples labeled as 0. For the testing validation, we're going to reserve a little smaller amount of data, real and fake. So we are here, we have the dimensions, and now just select a simple classifier, a neural network. With we will use some add-on optimizer, binary cross entropy for the loss, as it is a classification task, some metrics, and start training this classifier. After training the classifier, we can plot the metrics. We can see that when training, it keeps on improving the accuracy, but for the validation task, it also keeps off learning till reaching about a 50%. Of course, this is just with a little amount of data. But for example, if with a bigger amount of data, we keep on testing, or on training, sorry, and after training, we can see that the accuracy for the validation data reaches over 50%. That means that it's clearly able to distinguish between the synthetic data and the real data. So the synthetic data would be good enough to trick a classifier. And for the area under the curve, we've got, as we can see, a similar plot. Of course, we can also see here that it's almost overfitting the data, of course. The last test mentioned in the paper is checking for usefulness of the synthetic data. The idea is using the synthetic data for training an algorithm that will be able to perform decently on the real world with real data. And in order to do that, what we will try to predict is the last 24th step of our samples. You can see here we've got our data with rolling windows of 24 time steps. So we are going to take the 23 time steps to try an algorithm that is going to try to predict the last 24th step. For doing that, we prepare the data. We are going to do two options. One is training with real data and testing on unseen real data. And compare that, always using real data, with another option that is going to be training with synthetic data, that means fake data, and test the algorithm on the real world with real data. So we prepare the data. You can see here we've got 23 steps for training and try to predict the last 24th step. You can see here the training shape, the 24th step that is going to be predicted, of course 7 dimensions each, and also the testing validation. So we are going to define a basic function for creating a model, for building a model. And we will use the same model in both of the times. So let's go first to build the model. We are going to fit the model with synthetic data to try to predict the last step of the synthetic data, and we are going to validate this model on the real data using 23 steps to predict the last one. We train this, of course this is just as an example with a little amount of epochs and with a little amount of data. So this is the process that we should follow. The next is building the same model, but now we are going to use real data to try to use the first 23 steps to predict the last one. And the validation data is going to be also real, of course. That's our task, the real data. So after training this, we can plot the results, and you can see that that would be our task, to be able to use synthetic data to train a real algorithm in the real world to predict real data.